Welcome back to Chem 4300. In this video, we're going to finish up Chapter 8 on classical wave motion, and now we're going to turn our attention to 3D waves. So written in terms of Cartesian coordinates, the 3D wave equation looks like this. And here we see the partial derivatives with respect to x, y, and z, and here's the partial derivatives with respect to time on the right. And to solve this, we're going to take the approach we've been doing now for most of this chapter, is using the separations of variables approach, where we now have the functions split up into a product of x, y, z, and t functions. Plugging that into this, we find that there are harmonic wave solutions that have this form. So again, this is a quantity called the wave vector that is going to be important here, because this wave vector tells us the direction in which the wave is propagating, and that wave vector length is going to be 2 pi over lambda for that harmonic solution here, and this is the length of that vector. So if we start looking at these kind of waves, then really in 3D what we're looking at is our plane waves. But actually these are really just moving in one dimension, right? They're moving in one dimension along the direction of the k vector. But any type of 3D wave can be described in terms of these harmonic solutions. Sometimes it'll be convenient, sometimes it won't be convenient, depending on the symmetry of the problem. But these form a complete set of solutions that you can use when you're looking at 3D waves. Now, we also learned earlier how to look at the standing waves of in 1D with, say, a string bound at two ends, or a membrane in a rectangular box where the ends are forced to go to, amplitude of the wave function is forced to go to 0. And in this nice web app by Paul Falstad, you can look at the case of a 3D wave where the amplitude of the wave function is forced to go to 0 at the ends of the walls of a 3D box. And I'm going to leave it for you to explore this app, but it's more or less along the same lines as the other apps we looked at from Paul Falstad. What I want to focus on for the rest of this video is looking at waves in spherical coordinates. And so we learned already what the wave equation looks like in spherical coordinates, but now let's see if we can solve a problem in 3D. We've already done polar coordinates in 2D. So let's look at the wave equation in spherical coordinates. So here it is, very concisely written in terms of the Laplacian, but now the Laplacian operator, written in terms of spherical coordinates, has this form, okay, which we saw earlier in the last video. So we're going to again start with a separation of variables wave function, so a product of r part, a theta part, a phi part, and a time part. And now you can imagine the procedure here. So we're going to plug this into this equation here. We're going to calculate the effect of this Laplacian operator on this wave function, and then over here the derivative of time. And you can convert it into this form right away, where you can see that all of the spatial part is over here on the left. The time-dependent part is right here. For these guys to be equal, they have to be equal to a constant, which is the separation constant. Again, you can sort of know the drill at this point. So this gives us an ordinary differential equation for time. Now we go back and we focus on the spatial part, which is this partial derivative equation, so partial differential equation. And so written out, it looks like this. So what I've done now is I've pushed over to this side everything that depends on position r, and everything that depends on theta and phi is over here. And so since these guys have to be equal to this guy, and there's no crossing of the terms, so everything on this side to be equal to everything on this side means that it has to be equal to a constant, which is a separation constant I'm going to set equal to just lambda here. And that means I get an ordinary differential equation for the radial part. Okay, so now I'm going to go back to that radial function, and I'm going to do a change in variables. So this is kind of similar to what we did in the 2D circular membrane case. We're going to do a change in variables, and we're going to rewrite that differential equation so that it looks like this. In this form, a mathematician would recognize this as the spherical Bessel differential equation, whose solutions have been known for quite a while. And those solutions are the spherical Bessel functions, and they look like this here. And so there's two types. There's this J sub L and the Y sub L. And what we find is that our constant, our separation constant, lambda, has to become equal to L times L plus 1, where L is the quantity the index that characterizes each of these Bessel function solutions, these spherical Bessel function solutions. What these guys look like, if you're interested here, these are the J spherical Bessel functions, and they look kind of like the Bessel functions of the first kind, but they're a little bit different here. And here they are plotted out for J0, 1, and 2. And here are the other Bessel functions. This is Y0, Y1, and Y2. These actually go to minus infinity when you get to x equals to 0. But this is how these guys oscillate. So now let's turn our attention to the angular parts here. So we have the theta part and the phi part here. So taking that partial differential equation, I can separate it out and set it equal to this separation constant m squared, like I did before. So we get an ordinary differential equation for phi, which we know, again, has solutions like this, which are constrained to m values of 0, plus or minus 1, plus or minus 2. But so we've already worked through this problem, and what we're left with now is this theta dependence here. All right, so this part is I'm going to try to transform this one into a differential equation where the solutions are known. But so let's try to follow through some of the arguments here. So this is what it looks like here. What I want to do first to put this into a form where the solution is known is I'm going to make a change of variables. So I'm going to change the solution so that instead of as a function of theta, it's a function of v here, where v is cosine theta. So what I want to do is I want to differentiate with respect to cosine theta. So I want to try to remove this part here and make a substitution. So I'm going to show you how this is done. So we're going to define v as cosine theta. So the differential with respect to cosine theta, or v, we can rearrange here as d theta dv over d theta. Okay, so you can see those cancel out here. And this is the valid sort of chain rule type approach. And then we can flip this guy upside down, and we can evaluate that guy, and that ends up being 1 over sine theta, and we're left with this term right here. So this is relatively straightforward if you follow that sort of few steps there. Next, what I'm going to do is I'm going to multiply this guy times 1 minus cosine squared theta, or v squared, which is here. And since I have this result, which is this result, I'm going to plug that in over here. So I'm going to take 1 minus cosine squared theta times this for dv, and I get this. And then, of course, 1 minus cosine squared theta is just sine squared theta. And now we have it over sine theta. And now I have minus sine theta here. All right. Are you still with me? OK, so I made that substitution. And then finally, I'm going to take the derivative of this guy. So I'm going to take dv. So in other words, I know this is the operator that I've assigned with that. And it's going to be, and then 1 minus v squared dv is this guy. So if I plug in this guy here for that, and this guy here for this, then this all becomes this. And that is exactly what I have up here. OK. Now, I wouldn't ever expect you to figure that out on your own, but I want you to know that there is a simple proof, well, relatively simple proof here to show you that this term here with this change of variables can be converted into this differential equation here. And this differential equation is what's called the associated Legendre differential equation, and the solutions to this equation are called the associated Legendre polynomials. All right, so we know all the solutions to this differential equation. There are this particular function here, which I'll show you here in a bit. So these polynomials, they vanish for m values that are greater than L. The magnitude of m is greater than L. So that means that our m values, which were integer values plus or minus 0, plus or minus 1, plus or minus 2, and 3, and so on, are going to be now restricted to values from minus L to L in this case, because the other ones will vanish. And then taken together then with the phi part, then our solution, the product for theta and phi functions, is going to have this form here. And these guys are the associated Legendre polynomials. If you multiply them together, actually these guys end up being part of another function that's really common called the spherical harmonic functions. So this product of the theta and phi part show up over here with these actual effectively normalization constants to show up on the other side to create a set of functions called the spherical harmonics. All right. So this is just to introduce you to some functions that are going to appear over and over again in this spherical coordinate basis for looking at wave motion. So these associated Legendre polynomials, these are what they look like. This is a pretty big table here. Apologize for the small size, but you can look at it on the slides that you can download. And you can see here the L equals 0, the L equals 1, the L equals 2, 3, 4, and 5 forms. And these are what the polynomials look like. And they're all functions of cosine theta. And then here are the roots associated with these oscillating functions here. And you can probably easily plug these into any graphing app and plot what those look like, and you can find these roots yourself. Now those spherical harmonics, which we form from the product of the associated Legendre polynomials and our phi solution, are here, and these were actually discovered or introduced by Pierre-Simon de Laplace in 1782, and these are what these functions look like. And this is for L equals 0, 1, 2, and 3, and so on. So these are going to be really important when we get to quantum mechanics, but these are generally show up many, many years before quantum mechanics when you're looking at the solutions to the wave equation in 3D and spherical coordinates. So let's take a look at what these spherical harmonics look like. So there's a lot of them, so this can be a little challenging to sort of make it clear in your head. So let's just start slow with, say, the m equals 0 ones. These are the ones that are proportional to just the Legendre polynomials. So they don't depend on longitude. So when we're looking at this in spherical coordinate system, there's no longitudinal dependence. And so these are what are called zonal harmonics because the roots will divide the sphere into zones. So here you see this is the L equals 0, m equals 0. So this is a wave function where all of the wave function has the same sign all the way around the sphere for the spherical harmonic part. And then this is the L equals 1 where now it divides the wave function into zones. So the top hemisphere has one sign, the bottom hemisphere has another sign. But then when you get to L equals 2, then we divide it into zones where we have a top zone that's positive or one sign, the middle zone it's an opposite sign, and then the other zone has the opposite sign or the same sign as the top. And so now this continues, this is changing into zones, dividing into zones with increasing L. All right, so this is the case, just the case with m equals 0. Now, in the case for m not equal to 0 and m is equal to the maximum possible value, which is L, then we have no zero crossings at the latitude, and these functions are what are referred to as what's called sectoral harmonics. So again, just maybe go back a second here, remind you here. Here we were looking at, this was z and this was x, so we were looking in the z-x plane. So this is the North Pole and that's the South Pole, so to speak. And now we're going to look at them looking down. So if we're looking down, say, on the North Pole of a sphere, then this is what we get for L equals 0. M is equal to L. The absolute value of m is equal to L. This is a wave function where there are no nodes here. And then when we get to L equals 1, m equals L, then we get one node down the center. And when L equals 2, we get 2 nodes, and L equals 3, we get 3 nodes, and so on. So this is sort of similar to what we saw in polar coordinates in 2D with the m dependence, but now this is what we're seeing with, in this case, with the spherical harmonics looking down from the North Pole down, we see this sort of L dependence. In the case of the spherical harmonics where the absolute value of m is equal to L. Right. Now when you get to all other possible values of L and m, then what happens is we have a combination of those guys that divide the surface into what are called tesserae. And so these are what are called the tesseral harmonics. So the number of zonal nodes is L minus the absolute value of m, and the number of sectoral nodes is 2 times the absolute value of m. So this is sort of a off-angle view of the sphere, but this is now, these two images are a couple examples looking in the ZX plane. So this is looking sort of at the equator, so to speak, of a case where this is L equals 7, M equals 4. And this is looking down from the North Pole down onto the spherical harmonic wave function there for 7, L equals 7 and M equals 4. Okay. Now, one of the properties of spherical harmonics that makes them nice, this one I mentioned earlier that they were normalized. There was those extra terms in front of the angular and the theta and phi part that we derived earlier, is that these functions are satisfy this what's called orthogonality relationship. So if you integrate them, if you take the product of two spherical harmonics and you integrate them from 0 to pi for the theta dependence, it looks like I'm missing my d theta, d phi here. Sorry about that. If you integrate them from 0 to pi and then you integrate it from 0 to 2 pi, the integral comes out to be equal to 1, where this guy is defined as what's called the Kronecker delta product. These guys are 1 when M1 is equal to M2 and L1 is equal to L2. So this is, generally speaking, this is a kind of a delta function that we'll use that is called a Kronecker delta function that we'll use later in the course. And they have a simple behavior that when you have two indices equal, it's equal to 1. When two indices are unequal, it's equal to 0. So this tells us that when you do this integral and these product of these two guys don't share the values of L or M, then the integral is going to go to 0. So that means that with this sort of property here, we know that any wave function can be expressed in terms of the angular parts here, theta and phi, can be expressed as some linear combination of these spherical harmonics that's on the surface of this sphere. And similarly, we can use the orthogonality principle to decompose any wave function into its mode contributions here by doing this integral here. And here I have the full terms that should have been up here. All right, now finally what we're going to do is finish up this chapter by looking at the phenomena of diffraction and interference. And I'm only going to look at this in a very qualitative way. We're not going to get into any kind of quantitative detail how this occurs. But if you learn anything about waves early in your scientific career, you learn right away that waves have this property that they diffract when they pass through a slit. So if I had plane waves moving, they would hit some slit, and then they would undergo this behavior of diffraction where you see, here's an example where the plane waves hit the slit and then they diffract out. They form these circular patterns even though they come in as plane waves. And how much this curvature you have here depends upon the size of the slit. So if I made the slit bigger, then they'll still curve, but the curvature is very slight as they propagate through this slit here. Now, the other property that waves have is that they'll constructively and destructively interfere. So if I took two slits and I had a plane wave coming through, then essentially I have two sources of these curved waves here. And as they come out, then the regions where the wave crests meet, we have constructive interference. Where the wave troughs meet, I have constructive interference. But where a wave crest and a wave trough meet, I have destructive interference. So that's another property of waves. And what's interesting about these properties of waves and everything we've learned so far is that all of the waves we looked at required some medium, some mechanical medium that had some equilibrium value, and the wave was some oscillation in that medium, and as the wave propagated through, the medium just displaced away from some equilibrium value. So in the 1600s, Christian Huygens found that light diffracted and had constructive and destructive interference. So he could see this with light when he had appropriate size slits, and he can measure this interference patterns. And he realized that for light to interfere constructively and destructively and to behave like a wave, light must be there must be some medium in which this is occurring. And at the time that was kind of bizarre because people knew that light, or at least they thought that light, was just composed of particles. This was actually an idea that Newton had put forth, that light was composed of particles. So they didn't expect to see this kind of wave-like behavior. So they expected that light was particles, it shouldn't happen. And if you have a wave-like behavior, there should be some kind of physical medium that's being displaced away from its equilibrium value as the wave propagates through it. So at this point then, Huygens said, we need to figure out what this medium was. And at the time it was called the luminiferous ether. So the light was thought to be a wave based on this behavior, and it was propagating through something that yet unidentified medium that was called the luminiferous ether. And of course, the rest of the story will be continued in the next chapter. So to end up this chapter, I'll take a look in the next video at 2D wave interference patterns using, again, a really nice app by Paul Falstad.